In this video, I will show you how the fast and slow leg PWM works. So you can see that this is an inverter. So we have two types. So we have two legs. This is the fast leg, and then this is the slow leg. So the idea of the fast and slow leg is that this leg switches with the switching frequency, while this leg switches with the fundamental frequency of the AC voltage. So the reason why you want to use this switching strategy is because in rectified direction, where the current flows in the other direction, you can use just the body diodes instead of switching. So that reduces the losses a lot, and you can also get away with the cheaper MOSFETs here. Now, so basically a PWM strategy has a voltage that we want to generate, so it has a reference that we want this to be, and then we find the fast leg and the slow leg to get that voltage. So therefore, we should first find an equation for this VC. So VC, which is the converter voltage that the inverter generates, is equal to VMFL, which is this voltage. You can see that it's equal to here, and then minus this voltage, which is the slow leg voltage. So we know that these two voltages has the same reference point, the reference to ground here. So therefore we can just find VC by subtracting this one from this one. And now we want to find these two modulation voltages. So they can be determined by the gate signal. So VM FL, this should be equal to VDC times the gate signal. The reason for why this is correct is because we have, this is the VDC voltage. So when the gate signal is 1, this switch would be closed. So this voltage is equal to this voltage. So then we would have a voltage of VDC. And you can see that that is true for this equation. And if it's 0, this voltage will be equal to ground, which is 0. So then we would get 0. And we can do something similar for the slow leg. So this will be equal to VDC and then times the gate signal. So if we just insert this for the converter voltage, we would have VDC, and then we have the gate signal of the fast leg minus the gate signal of the slow leg, So both terms has a VDC, so I just factorize it out. So this is basically the equation for the gate signals. So you can see that down here, I've already written up those equations. So we have to simplify it even further, because the problem with this is that the gate signal here switches extremely fast. So we want to switch this with a duty cycle, which is basically, the definition of it is that it's the average of the gate signal over one switching period. So that simplifies it a lot. So then we would have that this becomes VDC and then times the duty cycle minus the slow leg, gate signal of the slow leg. So we don't want to change this with the duty cycle because it's already very slow. So now we have to solve for the duty cycle and the gate signal. So we know already the desired voltage that we want, and we know this one. So you can see that we have two unknowns and one equation. So what we want to do is that we solve for the duty cycle as a function of the gate signal. That will simplify it a lot. So we have that the duty cycle, dFL, is equal to, then we take, I just write VC, even though it's the reference, divided by the DC voltage, and then plus the gate signal. So this is what the duty cycle should be. But we are not able to solve it because this is a known. But if we add the constraints for the duty cycle and the gate signal, we are able to solve it. So we have that the duty cycle, this must be between 0 and 1. because the duty cycle is just the average of the gate signal for the fast leg. And the gate signal can either be 1 or 0. So the average cannot be outside of 1 and 0. And then this one can either be 0 or 1. So I have solved it down here. So we have just found this equation here. And then we know that this one is binary, while this is continuous between 0 and 1. So the only solution for this is then that slow leg is 0 when the voltage reference is larger than 0, and then 1 if it's lower than 0 or equal to 0. And if you try to derive it yourself, you will see that this is the only solution to this problem. And then we have the duty cycle here. So if we write up a block diagram of this, we will get this block diagram. And this is a block diagram you can just write straight into Simulink or whatever simulation tool you're using. So here I have some Python script to show you how the waveforms look like. So here I just defined some parameters, and then here is the reference voltage that we want, and here's the actual calculation. So the gate, you can see that the gate signal is 1 when it's lower than 0, and 0 if not. And then the duty cycle is calculated using the equation that we just found. So you can see that if we plot this, you can see that we get, so if we have a voltage of 400 volts and a sinusoidal reference voltage for the inverter, you can see that the gate signal is then 0 when it's above 0, and then 1 afterwards. And then the duty cycle would look like this. So it's sinusoidal for the first half period, and then we just shift it up for the second half period. So in my next video, I will show you how to make this in Simulink and simulate it. And this is a part of a course that I've made on bidirectional inverters. So it is a course where we look at how to control a inverter. And it works in both directions, so it could be a rectifier and an inverter, but we will focus on the inverter part in this course. So we go through 2 types of control methods, which is the ABC coordinate, which is basically a stationary frame. It's a simple one. And then a DQ coordinate, which is the one you, for example, use for grid-connected inverters. So here is the block diagram for the control in ABC coordinates. And here's the control circuit for the DQ. So if you're interested in this inverter course, go to the link in the description.